So, in our last class, we discussed about the other two end conditions of the column. So, in all, we have discussed so far about the four end conditions: hinged or pin-pinned condition, fixed free condition, fixed condition, and fixed hinged condition. In all these four conditions, we derived the relation for uh, the critical load or the crippling load, and we find that the values are coming quite different from each other. Now we can find a general equation which can represent all these cases, and we take the case of pin-pinned end as the ideal case when we obtain the equivalent length of the column for the other cases in terms of the formula of the pin-pinned end. So this was our formula for the pin-pinned end, that was pi square ei by l square. So instead of using the l length of the column, we used here the equivalent length of the column, and we tried to obtain the same formula that we have derived for different end condition by substituting the different length of the equivalent length for different end conditions. So as the formula itself is for the hinged condition, so for the both ends hinged case, the equivalent length should be equal to the length of the column which is given to us in the problem or numerical. So our crippling load will be simply pi square ei by l square. That is what we derived there. In the case of a cantilever column, or one end is fixed and the other end is free, that kind of condition, then the equivalent length of the column will be 2 times of the length of the column that is given to us. So when we substitute 2l there, we will get the formula for the cantilever type of column or fixed free column. So that comes out to be pi square ei by 4l square. When its both ends are fixed, in that case the equivalent length will be given by l by 2, giving us the formula as shown here. And when the one end is fixed and the other end is hinged, the last case that we can discuss, so the equivalent length should be l by root 2, so that it can give us the crippling load as 2 pi square ei by l square. So by remembering the equivalent length for different end conditions, we can obtain the values of the crippling load by using only single one formula that is given here. Now we had the formula like pi square ei by l square, that is we just discussed. So we know that the moment of inertia can be written as area of cross section multiplied by the radius of gyration square. K is the radius of gyration. So when we substitute here a k square and we bring this k in the denominator here, so that gives us l by k l whole square. Okay, so this l by k is basically slenderness ratio. Okay, this is termed as slenderness ratio. The length of the column divided by the radius of gyration whole square is called as the slenderness ratio. Now let's look at the limitation of the Euler's formula. While deriving the Euler's formula, we made the assumption that the stress is proportional to strain, or the material obeys the Hooke's law. So that means the stress that is being produced does not exceed the yield point limit for the compression. So for mild steel, the yield point limit for the compression is given by 320 Newton per millimeter square. And we know that the Young's modulus value for the mild steel is 200 into 10 to the power 3. So if we take up the formula of our crippling load, or PE, that is pi square E divided by L by K whole square, pi square EA divided by L by K whole square. So this is our formula for our crippling load. This is it. Yeah. So if we divide it by the cross section area of the column, so if you divide it here by A, and then A and A will get cancelled out, so what is left is the basically pi square E divided by L by K whole square, and the load, crippling load divided by the area, is basically the amount of stress or the compressive stress that is produced due to the application of the axial load. Now as we say that our material is obeying the Hooke's law and we have used that formula, so therefore this should not exceed the value of the yield point stress for the compression. So you substitute here that 320 should be greater than equal to the value whatever is here is on the right hand side. So when you substitute it here, the value for the mild steel is 200 into 10 to the power 3 for Young's modulus. So what remains here is that L by K comes out to be greater than or equal to 80 if you solve it. So what it is telling us? It is telling us that the slenderness ratio for the material, for this particular case, should be more than 80, and such columns will be called as long columns. If the L by K is less than 80, then we cannot use the formula pi square E A divided by L by K whole square, or the Euler's formula, in order to obtain the crippling load. So the applicability of Euler's formula is limited to a certain slenderness ratio depending upon the type of material that we have used and depending upon the type of end conditions that we are going to have. So we can calculate this limitation for each of the condition of the end conditions, or even for the different materials also. Like for the mild steel case, for the pin end, we have just calculated the slenderness ratio should be greater than or equal to 80. So that limits it. Okay, so the column should be long enough, or there its length divided by radius of gyration should be greater than or equal to 80 in order to be called as long column, so that we can apply the formula, Euler's formula. If it is less than 80, we can't apply it for the short column. So what happened actually, the values of the crippling load for the column given by Euler formula, and what we actually measure in the experiment, if you take up the compression test of the columns or strut machine, which is commonly called as strut machine. So if you put the column on the strut machine and you measure the crippling load, the load at, you start increasing the amount of load values, and you see, okay, at this particular load value the column start to buckle, and then you compare it with the Euler's formula, you find that there is a difference coming here. They are not coming out to be same. Furthermore, we find out that the Euler's formula is valid only for the very long column, or the columns which are having the slenderness ratio greater than 80, particularly for the mild steel. Okay, so based on these test results that we obtain in the experiment, there are certain empirical formulas which have been derived, and there are in fact plenty of them, and we are not going to discuss all of these empirical formulas, but the one which is very important, that is Rankine's formula, we are going to discuss today. So what we see here, that when a column is very short, okay, let's say the column is very stout column is there, L by K is less than 80 definitely for it. It may be, let's say L by K is only equal to 40, let's say, or maybe 30. So if it is a short column, so such a short column will never buckle actually. It will basically fail because of the crushing stresses or the compressive stresses. So for that, we know that the amount of load at which it will fail will be given by PC equal to sigma CA, where sigma C is the crushing stress or the yield point stress that you measure in the case of compressive testing machine. So through the compressive testing machine, so PC will be equal to sigma C into A. A is the area of cross section. You multiply it with the crushing point stress, you get the amount of crushing load that the column can sustain. And when a long column we can consider, which is having L by K much greater than 80, it will definitely not fail because of the crushing. It will buckle first. So when you start loading it at a certain point, it will start buckling rather than it will the failure due to the crushing stress. So for such a long column, we can apply the Euler's formula, that is pi square EI by L square. You can write here equivalent length also if you are talking about the other hand condition rather than hinged condition. So we see that for the short column, the load is given by PC equal to sigma CA. For the long column, it is given by P is equal to pi square EI by L square. What is in between them? What is for a column which is neither short or nor very long? So for these intermediate columns, the Rankine proposed the formula which is given by here 1 by PR equal to 1 by PC plus 1 by PE. This is what he proposed. PR is the load calculated on the basis of the Rankine's proposition. So PR is the critical load as per the Rankine's formula. So he says that 1 upon PR should be equal to 1 upon PC plus 1 upon PE. What this formula is telling us here. We see that for a given column, the value of PC, the crushing stress load, the crushing load is constant, because with the length it is not going to vary. It depends only on the crushing stress value sigma C and the area of cross section. For a given column of cross section is same, so PC is the constant. So 1 by PC is constant irrespective of the length of the column. But the Euler's crippling load pi square EI by L square is the one which will change with the length values. So we see that if we increase the value of the PE is equal to pi square EI by L square will increase with the decrease in length. So if L is small here, the value of PE will be more. You will get higher value of the PE. So the smaller and smaller the value of the length of the column, the higher the value of P you are going to get, and in that case the 1 by upon P shall be getting more smaller, okay, because P is getting larger, so 1 upon P will be smaller. So as 1 by P is much smaller in comparison to 1 by PC, okay, if 1 by P is very small in comparison to 1 by PC, I can safely say from this formula that 1 by PR will tend to 1 by PC, okay. So value of 1 by PR will be equivalent to roughly 1 by PC, because 1 by PE is much less than 1 by PC. So in that case we can say that PR is tending to PC. So your value of the Rankine load that you will calculate from the formula here given here will be tending more towards the value of near to the value that you calculate with this formula, okay. Now what will happen if the column is very long? So we see that when the column is very long, the value of L is high, so P will be small, so 1 by upon P will be much larger in comparison to 1 by PC. So in that case your 1 by PR value will tend towards the 1 by PE value, or PR value will tend towards simply equal to PE value. So the value that you will calculate from the formula proposed by Rankine will give us the value more closer to the value of Euler's load. So in this way, this formula covers the entire range from short column to the long column, and we can simplify it further. So we have this formula here, 1 upon PR is equal to 1 upon PC plus 1 upon P, and you simplify it, so it gives you PC plus P divided by PCP. So from this you can calculate the value of PR as PCP divided by PC plus P. You divide the whole numerator and denominator by PE, so that you can obtain this from, and then you substitute the value of PC and PE. So PC is sigma C into A, and PE is pi square EI divided by L square. For A also you can write as AK square, so A and A will get cancelled out. So what remain here will be, in the denominator will be 1 plus sigma C divided by pi square E into L by K whole square. This term sigma C divided by pi square E is constant for a given material, so we say that okay, it is small a, and the Rankine is constant, and we substitute the value here for the sigma C pi square E, sigma C divided by pi square E as a, small a, okay. So the formula for crippling load as per the Rankine's formula will be sigma C into A divided by 1 plus A into L by K whole square, where A is a constant for a given material because it is having the value of sigma C, crushing stress value for the material, the Young's modulus value, and pi is of course constant. So the value of this A is determined experimentally for different materials. So you have the value of sigma C and E for different materials. So you can keep on substituting the value of sigma C and E, and you can calculate the value of small a for cast iron, for mild steel and wrought iron as shown in this table. Remember, this formula is valid only for the hinged end, but if you want to convert it for the other end condition, instead of L we are going to substitute here LE, the equivalent length, and we know from the previous table what is the values of equivalent length for different end conditions in comparison to the hinged end. So that we can substitute here L by 2 or L by root 2 or twice of L, and you can obtain the Rankine's load value for the different end conditions by using the same value of A for the material that is given here. Now let's do some numerical, and this is our first numerical. Here we have been given that we have a column which is having a cross section I section, and we need to compare the buckling load that is calculated by the formula, Euler's formula, and the Rankine-Gordon formula. Sorry, I just need to tell you that the formula we just used here is also termed as Rankine-Gordon's formula. Okay, so either we say it Rankine formula or Rankine-Gordon formula, it is one and the same thing. So in this numerical we need to calculate the value of buckling load both by the Euler's load and Rankine load and compare it. That means we need to find the ratio between them. The length of the column is given to us as 400 centimeter, and it is pin jointed. The end conditions are given that it is pin jointed at both the ends, so it is hinge end. The yield stress for compression is given to us as 310, so that is the sigma C value that is given to us as 310 Newton per millimeter square. Young's modulus is also known to as 200 kN per millimeter square, and the Rankine's constant value small a is given as 1 by 7500. So we need to calculate first the Euler's load and then the Rankine-Gordon load using the formula for the Euler's formula and the Rankine-Gordon formula. Now in both these cases, either we use the Euler's formula or Rankine-Gordon formula, we need to find the moment of inertia for this cross section about which this column is going to buckle. You must have remembered the discussion we had in our last class that I told you that column will fail about the axis where its moment of inertia is less. Okay, so if you calculate the moment of inertia for this cross section about axis xx and both by the axis yy, you will find that it has a lower moment of inertia in the around the axis yy. Why is it so? That's quite obvious actually, because the material distribution from x-axis is quite far away from the axis, so that's why the moment of inertia will be higher in case of axis xx, while in the case of yy there is a lot of material which is around the axis itself, so it will be having the lower value. You can calculate and compare that also. We have done this exercise previously when we were doing the bending stress problems, so I'm not going to get into that detail, but we just simply say that okay, it is going to have the lower moment of inertia in the axis yy, and we can calculate the value of Iyy by using the formula that we have previously obtained in the bending stress section. So as you have these two sections here, okay, so these are both two sections are rectangular sections, so you apply the formula for the y axis, that is 2 times of the width of the section, that is 2, the depth is the section is 60, so BD cube divided by 12, so twice of that, so that covers these two area. Then what remains is this area, and this is 120. The length of this section will be 120 is total length, and you subtract from it 2 into 2, so 120 minus 4 is the width of this section, and the depth of the section is only 2. You can see here, this is the depth here, so depth is given here as only 2, so 120 minus 4 into 2 cube by 12, so that you put here, and then you calculate the value of Iyy as 7.21 into 10 to the power 4 millimeters 4. Area of cross section you can easily calculate by just dividing into separate rectangles in the same way. So the area of cross section will come out to be 472 millimeters square. Now you have the value of moment of inertia, you have the cross section area. You can calculate the radius of gyration by finding under root of I by A value, and the radius of gyration for this case will be 12.36 millimeter. Now first thing is first, let's start with the Euler's load, and we calculate the value of Euler's load here, that is pi square EI by L square. As it is having the hinged end, so simply L, the equivalent length will be equal to L, so we substitute here only L here. So after substituting the value of modulus of elasticity 200 into 10 to the power 3, the I value that we have calculated above there, and the length value as 400 centimeter, 400 into 10 whole square, we can calculate the crippling load as 8.895 into 10 to the power 3 Newton, or 8.895 kilonewton. Now the next thing is to apply the Rankine's Gordon formula. In the Rankine's Gordon formula, we have the value of compressive stress sigma c, yield point stress, so that is given as 310. Area we have already calculated. The Rankine's constant is given as 1 by 7500. We substitute here, substitute the value of length and radius of gyration, and calculate the value of Rankine's Gordon load as 9.778 kilonewton from this. Now if you compare them, that means you divide the Rankine Gordon load by the Euler load, you will find that is 1.099. So that means the Rankine Gordon formula is giving us the higher value of the crippling load in comparison to Euler's load. So here the Euler load is more more conservative. It gives us the lower value or conservative estimate. It says okay, the column is going to fail at 8.895 kilonewton, while the Rankine Gordon is saying no, it's going to last up to 9.778 kilonewton. So that is what we observed here. Now next question. In this numerical we are given that we have a 800 millimeter long column of alloy steel which has a area of cross section, rectangular area of cross section, which is having the width or thickness as 10 into 4. Okay, so 10 by 4 cross section is given, and the length of the column is given as 800 millimeter. The material is given as alloy steel, and it is mounted on strut testing machine with which is having the pinned end. So both ends are hinged, and you keep on increasing the amount of load. So you start increasing the load, and the material attains to the yield point of 300 megapascal. Okay, so that is the yield point stress for compression, that is sigma c. And then modulus of Young's modulus is given for the material for this alloy steel as 75 gigapascal. And what we need to do is we need to find the maximum central deflection. So in this case, when we have mounted this column on the strut machine and we start loading it, we start increasing the load. At certain point it will start buckling. So that is our critical load, or the buckling load, or the crippling load. So at this point, when it cripples, what is going to be the central deflection? That is what we need to calculate here in this numerical. So let's first write down those numerical value: the length value sigma c, width, depth of the section, and the Young's modulus. So as we discussed just now, that that the column will fail about the axis about which it has the least moment of inertia. So the least moment of inertia will be given by BD cube by 12. The another moment of inertia will be DB cube by 12. But because B is 10 millimeter and the depth is only 4 millimeter, so dB cube by 12 will be much higher than BD cube by 12. So we'll calculate the least moment of inertia for the section by using BD cube by 12, which will come out to be 53.5 millimeter to the power 4. Then we calculate the Euler's load by using the formula for Euler formula: pi square EI by L square. Equivalent length is equal to small l because it is a hinged end. You substitute the value of E, you substitute the value of I that you have just calculated, and the length of the column, and you calculate the Euler's load as 61.7 Newton. So this is the amount of load which can be applied axially on this machine, strut machine, before the column starts buckling, or the column starts buckling at this load only, right? So this is the maximum load that is being applied on this machine. So what will be the value of the bending moment because of this Euler's load? So we know that the bending moment is equal to load multiplied by the deflection. So as you remember that this is the case of our straight. This is initially straight, and this is our hinged end, and we have this, okay, we have pin end here. So we have pins here. So this is the kind of configuration we'll take. So this is the load P, and this is the deflection delta we have here. So the load is being applied at a distance delta from the central cross section. So exactly at the center we have the bending moment of the magnitude P into delta. So PE is the amount of load that we are applying, delta is the deflection that we have, central deflection we need to calculate here. So this is 61.7 times of delta. That is the maximum bending moment that will develop. Because of this bending moment, the amount of bending stresses that will be developed will be given by M by Z. You remember sigma by Y is equal to M by I. And what is I by Y? If you bring it here and you bring it in the denominator, I by Y is Z. So the maximum Y max you will take will be equal to D. So that is BD square by 6. So section modulus for the rectangular section is BD square by 6. You substitute it here. Bending moment you have just written as 61.7 into delta divided by BD square by 6. So that gives us the bending stress at the column. Now the central deflection we need to calculate. So we'll use that maximum stress. So maximum stress, we have been said that, okay, it is the maximum stress that is going to develop is 300 megapascal. So that is the maximum stress that we have been given here. Okay, so the maximum stress is equal to the direct stress, compressive stress that is being produced because of the axial loading, plus the bending stress. Okay, so because when we are applying the deflecting the column, so there is not only the direct stress, there is the bending stress also acting. We have just said that. So maximum stress 300 will be equal to direct stress. Direct stress is load divided by the area. So load we have just calculated, that is 61.7. Area of cross section will be 10 into 4. Bending stress we have computed from this, so we substitute it here. So the maximum stress will be equal to the direct stress plus bending stress, and we substitute those values here, and we calculate this part. It will be 1.543. We calculate this part here. This will be 2.314 into delta, and we can calculate the value of delta from this formula as 129 millimeter. So you see, by this way we can calculate the central deflection for the column. Okay, so this brings us to the end of our chapter, column and struts. Please do some numericals on this part also. And there are other empirical formulas which are given in books. You can see that there are Johnson for straight line formula, there is parabolic formula, and there are different IS and other codes also available for that calculation of the crippling load. So there are numerous such formulas which are available on based on the empirical relation, which we haven't discussed because they have been derived mostly directly from the experimental data, and they don't provide any other insight as the Rankine formula was providing us. So that's why we haven't discussed. You may go through those formulas also apart from the Rankine-Gordon formula. So we have Euler's formula, Rankine-Gordon formula, Johnson straight line formula, Johnson parabolic formula, and other code formulas are there. So please go through them so that you have the complete knowledge of the subject.